the entire test is discussed in strands, and this is the third strand, and this strand is geometry. We have two problems on each of the strands, and we have discussed the problems already for numbers and measurement. This is the third strand, and it is entitled geometry. Given the following square-based pyramid, respond to each statement below with either true or false. If the statement is false, write the correct statement in this space provided. Given the following square-based pyramid, respond to each statement below with either true or false. If the statement is false, write the correct statement in the space provided. That means if the statement is true, we just need to say that it is true and move merrily along. Before attempting to solve the problem, let us look at the basic features of a solid. We need to have an overview. We need to have an understanding. We have to have knowledge of all of the components of a solid before attempting to solve the problem. Because as a matter of fact, the problem that we have here is based on our knowledge and understanding of the features of a solid. A solid is defined by its faces, edges, and vertices. Any plane or curved surface of a solid is called a face. Any surface of a solid is called a face. Any plane or curved surface is called a face. The solid is sitting on one of its faces, so we are taking a look at faces first of all. The solid is sitting on one of its faces. That face may be called the base. So there is the first face that we are discussing. It is called the base, and it is the base because the solid is sitting on that face. That face is called the base. We have two faces in the background. So let us take a look at those faces. We have faces in the background, two of them. Those are the two faces that we have in the background. There are two faces in the foreground. If the solid is not transparent, it will hide the other faces. So by placing the faces right there, we realize that the other faces are hidden. So we have the first face is the base. Then we have two other faces in the background, and finally we have two faces in the foreground, and those faces, if the solid is not transparent, will hide the other faces. So we have taken a look at all of the faces of the particular solid that we are discussing at the moment. So what we have done is ensure that you have a glance at all of the faces like that. All of the faces, the base, the two faces in the background, and also the two in the foreground. One solid that is an exception to the way that most solids are defined is the cone. So the cone will be an exception in a few cases to the way that we define solids. It has a curved face that goes all the way around. A curved face. Apart from the circular base of the solid, its entire surface consists of a single curved face. The cone has two faces, the base on which it sits and a curved face. So it is saying that apart from the circular base that we have for that cone, the entire surface consists of a single curved face. There we are taking a look at the circular base of the cone. The base of the cone is circular, and that is one face of the cone. And the other face of the cone is the large curved face that we have in blue right there. Now let us take a look at the vertices. We have faces, vertices, and edges. We have taken a look at the faces. Now we are taking a look at the vertices. One is called a vertex, and the plural of vertex is vertices. A vertex is any location where a face is reduced to a single point. Generally, a vertex is a point where faces meet. Let us take a look at one of the faces of the solid. So, there we have one face. Let us see how that face can be reduced to a single point. It is disappearing, reduced to the single point that we have here, and that single point is the vertex. That is your vertex. That point to which the face disappears is a vertex. Also, it is a point at which four faces meet. Let us highlight the other vertices. But before we highlight the other vertices, remember that we took a look at the faces, and apart from the one that is actually the base, we had two in the background and two in the foreground. And all of those faces meet at that vertex. Let us highlight the other vertices. There we have them. Where faces meet, a point where faces meet. Again, we will take a look at the cone as an exception to the other solids. The cone has a single vertex. Just one vertex that cone will have. Also, that single vertex is not a point where three or more faces meet. As a matter of fact, there is only a single curved face, which is reduced to a single point as we move up. So we have only a single curved face on the cone, and as we go up, it diminishes into the point that we have there, that single vertex. Now we will take a look at the edges. An edge of a solid is any line that is straight or curved where two faces meet. Any line where two faces meet is an edge of the cone. Any line where two faces meet is an edge of the solid. So we have two faces that meet. The line along which those faces meet is an edge of the solid. The two faces meet along this line. That is an edge of the solid. Now we have removed those faces in order that we might see the other edges. Let us highlight the other edges of the solid. So we are inserting there the other edges of the solid. And at each of those edges, two faces meet. Those represent lines along which two faces meet. An edge is like a crease on the solid. Every crease on a solid is an edge of that solid. So it is as if we crease the solid, and where we have that crease, it is the edge of a solid. And it is more appropriate to say that it's a line along which two faces meet. The cone has a single circular edge. So there is your single circular edge. It is where the base of the cone meets the curved face of the cone. At that edge, the curved face meets with the circular face that is called the base of the cone. So the circular face, which is the base of the cone, and the curved face of the cone is, we are looking in 2 dimensions, so we cannot see the curved face right here. But I am sure that in your classes, in your home, anywhere there is mathematics, you are capable of viewing a cone and you have an appreciation of its curved face. So the curved face meets with the base of the cone, and that is what we have there, the single edge of the cone, the single circular edge. The way in which the cone is consistent with other solids is that its edge is also a line along which two faces meet. That's true for every solid, and it is also true for the cone. However, its circular edge still distinguishes it from other solids. So the circular edge that we have for the cone distinguishes the cone from other solids. That's a distinction that only the cone has. So let us take a look at the statement of the problem. I am sure that we would have recalled a few things from the previous slides, but let us take a look at it again. Given the following square base pyramid, respond to each statement below with either true or false. If the statement is false, write the correct statement in the space provided. The statement A is, the solid has 4 vertices. The solid has 4 vertices. Does the solid have 4 vertices? Of course, we defined and identified vertices earlier on. So let us look at the number of them that we have in this solid. So we are going to number them. 1, 2, 3, 4, 5. There we have 5 vertices. If the statement is false, write the correct statement in the space provided. This one is false because we have 4 vertices is what the statement of the problem is saying, and we say that the statement of the problem says 4, but we know that we have 5 vertices. So because we have 5 vertices and the statement says 4, we know that the statement is incorrect, and we may write the correct thing in the space provided. Since the statement is incorrect, let us write the right thing. That's what we need to do. It is false. The solid has 5 vertices. And we saw that the solid has, and we can see them still highlighted there. 1, 2, 3, 4, 5. The solid has 5 vertices. For a solid that has only plane, or what we say flat faces, a vertex is said to be the point where 3 or more faces meet. So when this solid has flat faces, or what we call plane faces, then for that solid, a vertex is said to be the point where 3 or more faces meet. And we have 5 of them. The statement of the problem say 4. We are sure that that statement is false, and we have included the correct statement. B. The solid has 8 edges. How many edges? Let's see. We know that an edge is where 2 faces meet. The line along which 2 faces meet. We define and identify edges earlier on. Let us number them. So all of those edges, 1, 2, 3, 4, 5, 6, 7, 8. So we have read there 8 edges. The statement says 8, and we have 8 of them. The solid has 8 edges. When we counted them, we got 8. The statement is true. What do we do if the statement is true? If the statement is false, write the correct statement in the space provided. But the statement is true, so we only need to say that it is true, and there's nothing else to do. We may write true in the space provided. Since the statement is true, we do not need to make any additional statement. So, only if the statement is false, we need to say the correct thing. Since it is true, we do not need to say anything else. We do not need any further discussion. C. The solid has no equal triangles as faces. The solid has no equal triangles as faces. Look at this. Square-based pyramid. This is saying 2 things. 1, that the base is not a triangle. It is a square. And 2, since it is a square, all of the sides are equal. So we are sure that the edges that we have here are all equal in length, since it is a square base pyramid. In this problem, we are focusing on the triangular faces. The solid has no equal triangles as faces. So we are focusing our attention on the triangular faces. We have taken a look at the faces. We will take a look at only the triangular ones in this particular case, and we will also count them. First, take note of the two hindermost faces. Do not forget them, the ones at the back. And we also will take a look at the ones at the front. They will block the ones at the back, but we know we have two of them, so we will put those two new faces in and we will count them also. So they are part of the count. So we are at 4 of those faces. We have 4 of them. There are 4 of them. Apart from the base, which is a square, all of the other faces are triangular faces. But we still have not answered the question or responded to the request. The solid has no equal triangles as faces, but we have already identified the triangles. We need to take a look at if they are equal or not. So we need to know the length of each side of the triangle. We are focusing on the triangular sides, and we are also focusing on the fact that the base is square, as we said before. The base is square, and we are focusing on the triangular faces. Since the base is a square, it means that all of the sides are equal. All of them are equal, since it is a square. In order not to cause this slide to be cumbersome, we will not include all of those measurements on the next slide. We are working on the slide and we are doing demonstrations, we are doing illustration, but while doing so, we cannot cause the diagram or the slide to be crowded so that the students will not be able to distinguish one thing from the other. We like to keep the detail visible, identifiable, and also distinguishable. So we will not include every single thing in there. We will not include all of the dimensions. We still need to bear them in mind as we discuss the measurements in this 3-dimensional diagram. So in order not to cause this slide to be cumbersome, we will not include all of those measurements on the next slide, but we need to bear them in mind as we discuss the measurements in this 3-dimensional diagram. We know that all of the sides of the base are equal, or all of the edges of the base are equal in length. But we need to also take a look at the slant measurement of 7 centimeters. That slant measurement of 7 centimeters is also a part of the triangles. So we need to bear that in mind and we need to take a look at it. 7 centimeters is the length of every edge that joins the base to the apex. So this is the base. We have the base, square base, and we have the apex, that vertex. At the top is the apex. We have edges going from base to apex, base to apex, base to apex, base to apex. And we are saying that each one of those is equal to 7 centimeters. So we will highlight all of the edges and include the measurements when they do not cause the diagram to be too fussy. We are trying to put as much information on the diagram for clarification, but if it is too fussy, then we will be defeating the purpose. So this is 7 centimeters, and each of those edges that joins the base to the apex, each one of them is equal to 7 centimeters. All of the triangles in the diagram have one side of 5 centimeters and other two sides of 7 centimeters each. So each triangle, of course, because each triangle is formed by the base and two of the edges, then we will know that 5 centimeters is the length of one side of the triangle, and that the other two sides will be 7 centimeters each. Each of the 4 triangles in the diagram will therefore look like this. Each one of the 4 triangles, that's what each one will look like. Each of the 4 triangles will look like the one that we have there. 5 centimeter for that dimension, and of course the other two will be 7 centimeters each. We are extracting this triangle from the solid, where we have this is 5 centimeters and the slant lines that we have here, each of them is 7 centimeters. 5 centimeters is the length of the side of the square base, and 7 centimeters is the slant height of the pyramid. Five centimeters is the length of the side of the square base, like right there. And 7 centimeters is the slant height of the pyramid, right there and there, which will be these two. Diagrams are not usually, or we may say that they are not always drawn to scale. And in a 3-dimensional diagram, the lengths are not usually proportionate. We will have to understand the 3-dimensional figure and understand its dimensions and its basic features in order that we can come to the conclusion that we need to come to. And we have to do that despite the fact that it is not generally drawn to scale. And also in a 3-dimensional diagram, the lengths are not usually proportionate. But what we are acting on principle. If we act on principle, on knowledge, on understanding, then we will know the lengths that are the same in a 3-dimensional diagram, and we will know the size and shape of each face. There are 4 triangles that have the same measurement as the one below. That triangle will have the same measurement. Why? Because the base here is 5 centimeters. We have the 5 centimeters there. And each slant height will be 7 centimeters will go there. 7 centimeters will be right there. And 7 centimeters will be right there. So we are sure that the two that we have in the background will have the same measurements as we have there, and also the two in the foreground. This will be 5 centimeters and these two will be 7 centimeters each. The statement is false. The solid has no equal triangles as faces. but we are sure that it has 4 equal triangles as faces. So we say that the statement is false, and if the statement is false, write the correct statement in the space provided. So let us write the correct statement. It has 4. The solid has 4 equal triangles as faces. In a 3-dimensional diagram, actual measurements are not what they look like. And as we said before, we need to extract the true measurements and the true faces, the true sizes of the faces from a 3-dimensional diagram. And it means that we have to have a good understanding of the construction of that particular diagram. Each diagram is based on a particular principle, and if we understand the principle, then we will know the size and shapes, the sizes and shapes of all of the faces. In analyzing a 3-dimensional diagram, we need to make use of the actual measurements and not what they look like. So we need to be aware of the actual measurement and not what they look like. And we will make use of the actual measurements by understanding how the 3-dimensional diagram is constructed and understanding the principle on which a 3-dimensional figure is based. Architects and contractors who work with 3-dimensional diagrams make use of 2-dimensional views for simple reference. So the architects, the draftsmen, the contractors, they all make use of 3-dimensional diagrams. However, the 3-dimensional diagram will be accompanied by 2-dimensional representation of some of the features of the diagram. Viewing the object from above is called the top view or plan, and that will be in 2 dimensions. The view that we call the plan is a top view, or the top view is called a plan or the plan. This is what the object looks like from above. So if you are viewing that square base pyramid from above, that is what it will look like. You will see obvious that this base is a square. The base is a square of side 5 centimeters. We may show all of those measurements. The base is 5 centimeters. 5 centimeters each side of the square. The slant edges of 7 centimeters go from the base to the apex, and we will show all of those slant heights. They go from the base to the apex. Those measurements will be 7 centimeters, and it will not be drawn to scale necessarily. Show the apex. We have the apex right there. So the apex will appear to be a point in the middle of the diagram, and the slant height will come together to form the diagonal of the square. From the plan, it is easy to see that all of the triangles are congruent and their measurements are also more obvious. So looking at the pyramid from above, it is more obvious that all of these are equal to 5 centimeters. It is also obvious that all of the triangles are congruent because we will have 7 centimeters here and here we will have 7 centimeters for these two sides, and we will have the additional side of 5 centimeters, and that is going to be the measurement for every single triangle that we have there. Although the measurements are obvious, this plan still cannot be a scale drawing. Right? It is not a scale drawing, but it causes the dimensions to be more obvious. It causes the measurements in each triangle to be more obvious. This is because of the slant edges in the object. So it cannot be to scale because of the slant edges. The slant edges, when we reproduce them here, is not going to be in the proportion that they are in the actual solid. And of course we know that in the actual solid, when we have a three-dimensional representation of that solid in two-dimensional space, we know that the measurements are not proportionate. Sometimes a plan or top view may be a scale drawing. Sometimes the front, side and back view are called elevations and may also be scale drawings. So the elevations can be scale drawings, but the plan is not necessarily. As a matter of fact, the plan can be a scale drawing, but in this case it is not a scale drawing, and what causes it not to be possible to be a scale drawing is that the edges that we have here are slant, like this. They are slant. That is what will prevent the diagram from being a scale drawing. But if we just have horizontal and vertical representations, surely the plan might be a scale drawing. So we have the front, side and back views are called elevations and may also be scale drawings. So those two-dimensional representation of a three-dimensional diagram may be scale drawings. Recall the plan and elevation from the previous slide. So we are placing them here just as a reminder of the dimensions that we had. The statement is false. The statement that we have here for statement B, the solid has no isosceles triangles as faces. The solid has no isosceles triangles as faces, but we are sure that these triangles are isosceles. An isosceles triangle has at least two equal sides. And we see here that the triangle, each one of them has two equal sides that are equal to 7 centimeters, which is represented in the three-dimensional diagram as the slant height of the pyramid. The statement is false because all of these triangles are isosceles with these sides both equal to 7 centimeters. So we are sure that all of the triangles are isosceles, and we have 4 of them. Any triangle with at least 2 equal sides is isosceles. Those are isosceles triangles. The solid has 4 isosceles triangles as faces. From the plan, all 4 isosceles triangles are obvious. Each of the triangles has 2 equal sides. From the plan, all 4 isosceles triangles are obvious. Each of the triangles has 2 equal sides. Statement D. Opposite sides of the base in the solid are not equal in length. That's what it says. That the opposite sides in the base of the solid are not equal in length. Square based. From the statement of the problem, we see that the base of the solid is a square. All sides of a square are equal. Therefore, opposite sides must be equal. All sides of a square are equal. Therefore, opposite sides must be equal. So, we have this and its opposite. This one and its opposite. They are equal. This one and its opposite. They are equal. And as a matter of fact, they are all equal in length, since the base of the pyramid is a square. The statement is therefore false, and according to what we have here, if the statement is false, write the correct statement in the space provided. So let us write the correct statement in the place provided. Opposite sides of the base in the solid are all equal in length. So, opposite sides of the base in the solid are equal in length. That is the correct thing. We will take a look at problem number 6. Each shape below has side lengths labeled in units. Determine the number of lines of symmetry of each shape and then place a tick in the correct box. Each shape below has side lengths labeled in units. Determine the number of lines of symmetry of each shape and then place a tick in the correct box. So we have all of the shapes here, and the heading is shape and number of lines of symmetry. None, only one, exactly two, exactly three, exactly four, more than four. So we have the options which will tell us the number of lines of symmetry that the object has. So if the object has 10 lines of symmetry, then we have to say that is more than 4, and we will have to put a tick in this box. If there is none, it does not have any line of symmetry, we will place a tick in this box. And if it has exactly 3, we will place a tick in this box. But in order to determine the box that we will put a tick in, we will discuss line or axis of symmetry. We will take a look at what that means. In order to solve this problem, we need to understand what a line of symmetry is. On the next few slides, we will take a look at lines or axes of symmetry and their meaning and implication. So we will take a look at the lines of symmetry and what they mean and what they will cause. So we will look at the causes and the consequences. A line of symmetry is one which divides an object into halves, two halves that are mirror images of each other. So the line of symmetry will divide the object into halves that are mirror images of each other. Also, if one half of an object is reflected in its line of symmetry, then the other half will be obtained in such a way that we will get the entire object. So in order that we, as long as it is symmetrical, as long as there's a line of symmetry, a line or axis of symmetry, if we reflect the object in that line of symmetry, the one half of that object in the line of symmetry, then the other half will be generated, and that will give us the entire object. So take that heart, that is your object, and that is your image, and we have the entire heart. Right, so one half will be the object, and the other half will be the image, and that will be the entire object. So the line of symmetry will divide the object into halves that are mirror images of each other. If an object is reflected in a mirror line, it is as if it is flipped over or inverted. If an object is reflected in a mirror line, it is as if it is flipped over or inverted. Inversion does not mean that it is upside down. Inversion may mean that it is the other way around, or we may say that it is flipped over, or it is switched around. In mathematics, something that is flipped over sideways is also inverted. We say that it is laterally inverted. It's flipped over sideways, that's laterally inverted, and an object and its image that we have here in a mirror line, they are lateral inversions of each other. That means it is the other way around. If we use the mirror line as a pivot, then it is as if we flipped it over. Notice that when one side of the heart is flipped over, the other side is formed. That is the effect that a mirror line should have on an object, and the line of symmetry on each side of an object. The same effect that a mirror line has on an object is the same effect an axis of symmetry should have on each side of an object. So the axis of symmetry of the object will result in one half of the object being a mirror image of the other, and if it is a mirror image of the other, then it is as if it is flipped over sideways or laterally inverted. Notice that when one side of the heart is flipped over, as we said before, the other side is formed. That is the effect that a mirror line should have on an object, and the line of symmetry on each side of an object. If we reflect the triangle that we have there in the mirror line, we say that the original triangle is laterally inverted. The triangle and its image will form an object that is symmetrical about the mirror line. Right, so if we have a triangle, we reflect the triangle. We say that it is laterally inverted. And if we put that together with the original triangle, then an object is formed that is symmetrical about the line of symmetry, or the axis of symmetry. The mirror line is therefore called a line of symmetry. Students are required to be visually familiar with an object and its image relative to a mirror line. As such, they should be able to tell if an object is symmetrical about a particular line. If an object is symmetrical about a particular line, then that line is called a line of symmetry. Let me read that again. Students are required to be visually familiar with an object and its image relative to a mirror line. As such, they should be able to tell if an object is symmetrical about a particular line. If an object is symmetrical about a particular line, then that line is called a line of symmetry. You need to be familiar with the mirror line and the effect that the mirror line will have on an object in forming the image of that object, because the axis of symmetry acts as if it is a mirror line in which half of the object is reflected in order to form the entire object. That is what a line of symmetry is. A line of symmetry is like a mirror line in which half of the object is reflected in order that the other half may be formed. Put those together and we will get the entire object. Reflect half of that object in the mirror line and we will get the entire object. When the entire object is formed, then the mirror line in which one half is reflected in order to generate the other will be a line of symmetry. Here we have another object that is formed by reflecting one half of it in its line or axis of symmetry. And that is how we might form objects, by reflecting one half of it in the axis of symmetry. And if it is not formed that way, as long as there is an axis or line of symmetry, then we know that one half of the object is a mirror image of the other. Our first diagram is a square, and we are attempting, as required by the statement of the problem, to find or to determine or to be able to count or report all lines of symmetry. The first diagram is a square. How do we know that it is a square? Because we have four sides here, but that does not make it a square. We have four right angles. We have four right angles. That does not make it a square. But when we have four right angles and these adjacent sides are equal, then we know that all sides are equal. Its length and width are equal. It is a quadrilateral with all angles equal and are right angles. So as long as all angles are right angles and adjacent sides are equal, then we are sure that all of the sides are equal, and that figure is a square. A square may be divided into halves that are mirror images of each other. A square may be divided into halves that are mirror images of each other. How do we know that? because we can take 1/2 of a square and reflect it in a mirror line, and the other half will be generated in such a way that we receive the entire figure to be a square. So a square may be divided into halves that are mirror images of each other. A square may be formed by reflecting 1/2 in a mirror line, which is called the axis of symmetry. The axis of symmetry that we have seen is a bisector of opposite sides. So we have the axis of symmetry, this one, it bisects opposite side. That means it divides the opposite sides in 2 equal parts. It divides this side in 2 equal parts. It divides this side into 2 equal parts, and they are opposite sides. So the bisector of opposite sides is a line of symmetry. That's what we are saying. And we are also saying that the other bisector of opposite sides will be another axis of symmetry, which is that one. That one will also be another line of symmetry. We have taken a look at the bisector of opposite sides, and those are 2 axes of symmetry. So we will take a look at any more that we can find, and we have the statement here that we'll take a look at 2 more. We should be able to find 2 more. We may also show that a diagonal of a square is also an axis of symmetry. So the square on this occasion is divided into 2 equal parts that are mirror images of each other along the axis of symmetry. That is the line of division. And as we see, one side is a mirror image of the other. Therefore, we have the diagonal to be an axis of symmetry. Reflect 1/2 of the square in a mirror line that is a diagonal of the square, and the entire square is formed. That's what we have done. Reflect one side of the square in the diagonal, and the other side or other half will be formed. And we are sure that the diagonal is a line of symmetry. The other diagonal of the square is a line of symmetry. It is a line of symmetry also. So there we have another 2 lines or axes of symmetry, and those axes are the diagonal of the square. A square therefore has 4 lines or axes of symmetry. So we will go to exactly 4, and we will place a tick right there. The first shape is a square, and we have seen that a square has 4 lines or axes of symmetry. Exactly 4. So we go to exactly 4, and we are in the same row as the square. The tick needs to go right there. In the same row as the square, place a tick in the box that is in the same column as the heading that says exactly 4. What about the other shapes? the other two shapes do not have any axis of symmetry. For the two objects, we may not draw any line that divide them into halves that are mirror images of each other. We may not draw any line that divide them into halves that are mirror images of each other. Also, if we fold the object onto itself, like closing a book, then the crease that is formed, which divides the two identical halves, will be the axis of symmetry. So we are saying something apart from the fact that we are saying that these two do not have any line of symmetry. But we are also saying if we fold an object onto itself, like closing a book, then the crease that is formed, which divides the two identical halves, will be the axis of symmetry. Also, if we fold the object onto itself, like closing a book, then the crease that is formed, which divides the two identical halves, will be the axis of symmetry. Experience working with axes of symmetry should make it obvious that there is no axis of symmetry, but pay attention to the following tests. We are saying that these two do not have any axis or line of symmetry. We are also saying that if you fold an object onto itself, the crease will be the axis of symmetry. But if you fold it and it does not fold onto itself, or it cannot be folded onto itself, then it does not have any axis of symmetry. We are also saying that our experience working with axes of symmetry should make it obvious that there is no axis of symmetry that we have in these diagrams here. But we will take a look on other slides that will demonstrate that they do not have any axis of symmetry. For triangles, draw a line through a vertex that bisects the opposite side. Now, if there is any axis of symmetry of a triangle, of any triangle at all, that axis of symmetry must pass through one vertex and bisect the opposite side. So what we will do is draw a line that goes through one of the vertices and bisects the opposite side, like that one. Now, that's the only way that we can draw an axis of symmetry that passes through this vertex or also bisect this line or this side. That's the only possible way. Now, by actually drawing it, we will see that that one is not a line of symmetry. If that line does not divide the object into halves that are mirror images of each other, then it is not an axis of symmetry. So does it? So we have the two halves represented by those two triangles there. So we will separate them from the object in order to have a better look at them. Because if this is a line of symmetry, then first these two triangles will be congruent. However, if they are congruent, it does not make the line a line of symmetry. They will have to be first congruent, and then one will have to be the mirror image of the other. So if they are not first congruent, then we can forget about calling the line a line of symmetry. because if they are not congruent, it is impossible for one to be a mirror image of the other. For one to be a mirror image of the other, they have to begin by being of the same shape and size. So they have to begin by being congruent, and they are not congruent, so we are sure that that line is not a line of symmetry. Since they are not congruent, we will not go any further. If they were congruent, then further, one would have to be the lateral inversion of the other. Since they are not congruent, they cannot be mirror images of each other. And if they are congruent, for them to be mirror images of each other, one has to be the lateral inversion of the other. And lateral inversion was discussed earlier on. In a triangle, any line of symmetry has to go through a vertex and bisect the other side, or the opposite side. There we have another line going through the vertex here and bisecting that side. Insert two elemental triangles into which the object is divided. Those are your two triangles. Separate them from the object in order to have a better look at them. There we have them. They are not of the same shape and size, much more mirror images of each other. The dotted line is not an axis of symmetry. It is obvious that those two triangles are not congruent, and they have to begin by being congruent. And yet still, being congruent is not enough. One has to be a mirror image of the other, or a lateral inversion of the other. There is still another possible axis of symmetry. However, by now we should all have an understanding, and we will not bother to place it under the microscope. So there's another one that will go from here down to there, but we will not include that one. Instead, we will spend our time looking at the parallelogram that we have there to see if we have any line of symmetry, or if we can show that we will not have any line of symmetry. For quadrilaterals, we may try diagonals and bisector of sides. So, if this quadrilateral or any quadrilateral at all will have an axis of symmetry, it will have to be either a diagonal or bisector of sides. So what we will do, we will include those bisectors of sides and also the diagonals, and see if the diagonals are actually lines of symmetry. That is, if they divide the object in halves that are mirror images of each other. There we have a diagonal. The line divides the object into congruent halves. So that's where we start. The line divides the object into congruent halves. Like that. It is still not an axis of symmetry because the halves are not mirror images of each other in the dividing line. If we flip this over in this line over to this side, it will not fit onto this one exactly. So because it will not fit onto this one exactly, then we know that this is not a mirror image of this one in the mirror line, or in the line that we have there. For the halves to be mirror images of each other, the line that joins an object to its image must be perpendicular to the mirror line. So we have two halves that are congruent. That's a good place to start. But let us say that the only two corresponding points that we can find are the vertices here and there. Those are corresponding points. We don't see any other point that could ever be corresponding points, so we will have to use those two. If we draw a line from one to the other, like that, for this half to be a mirror image of this half, then when we draw the line straight across for corresponding points, then that line must be perpendicular to this one. If this one is not perpendicular to this one, then we do not have a line of symmetry. So all of these angles need to be right angles, else the line is not a line of symmetry. The line that joins a point to its image is not perpendicular to the mirror line. Those angles are not equal to 90 degrees. Because those angles are not equal to 90 degrees, the angle, that is the angles that are formed by the proposed mirror line, it is not a mirror line, by the proposed axis of symmetry and the line joining a point to its image, those have to be perpendicular to each other. Since they are not perpendicular, then we know that we do not have a line of symmetry. We may conclude that the halves are not mirror images of each other. The line is therefore not an axis of symmetry. And of course, although the line is not an axis of symmetry, we know that the triangles are congruent. They are congruent, but the line is not a line of symmetry. We should not have to test the other diagonal. You know, with time we gain experience. With time we gain experience, and we know that if one diagonal is not an axis of symmetry of a four-sided figure, that is, then we know that the other diagonal surely will not be a line of symmetry, because the principle that we have discussed before still holds, because the lines that we are going to draw will actually be the two lines that we had before. Again, the line divides the object into congruent halves. It is still not an axis of symmetry because the halves are not mirror images of each other. The mirror line and the line joining a point to its image will be the same lines as before. So the mirror line is the one that we have here, which in the first diagram was the line that joined the point to its image. But this case, the line that joins the point to its image is actually the line that we attempted to use for the axis of symmetry on the previous slide. So the two lines turn out to be these two lines that we have used before. And by using them, we concluded that the angles are not right angles. And because the angles are not right angles, then one half is not a mirror image of the other half, and the line is not a line of symmetry. Next slide, we will take a look at bisectors of parallel sides. On this occasion, we will test a bisector of parallel sides. There we have a bisector of the parallel sides. The line divides the object into congruent halves. Of course, we can see that these are congruent. It is still not an axis of symmetry because the halves are not mirror images of each other. How do we know that they are not mirror images of each other? For the halves to be mirror images of each other, the line that joins an object to its image must be perpendicular to the mirror line. So if we put 2 points there, corresponding points, and we draw a line like that, then that line, what we propose to be the mirror line, that one is not perpendicular to it. All of these angles are not right angles, so this is not perpendicular to the dividing line. Therefore, the dividing line is not an axis of symmetry. We may conclude that the halves are not mirror images of each other. The line is therefore not a line or axis of symmetry. The other two objects do not have any line or axis of symmetry. In the rows that contain the two objects, place a tick in the column with the heading that says none. Right, there is none. This has 4 lines of symmetry, and each of these will not have any. Now we have come to the conclusion of another audiovisual presentation of Richard James Mathematics Resources, and it is my hope that you would have gathered quite a bit of information, especially about mirror images, lines of symmetry, mirror halves of each other, lateral inversion, and all of those. And it is my hope that you will be able to transfer those bits and pieces of information, knowledge that you have gained, into other subject areas and also other topics in this same subject, mathematics.